do not have a huge long 2-hour presentation, so please feel free to ask questions at any time. Unfortunately, if you heard Sarah and Brian's talk this morning, you probably heard half of my talk. I'm here to say that what they said works. Anyway, for those of you who don't know me, my name is Damien Gray. I am an industrial physicist. I spent about half my life doing industrial physics, the other half working here at NI as a LabVIEW programmer. So I'm kind of straddling both fields right now. I am a laser optics engineer at EOS North America, which is up in Pflugerville. EOS is one of the older 3D printing companies in the world. They were incorporated back in the late 80s, along with about 4 others. And this project, interestingly enough, is not, even though I'm currently working for EOS, this project was not done there. It started off being done, it started off early 2015. I was hired by Stratasys, which is another one of the old 3D printing companies that was incorporated in the late 80s. And they decided they wanted to do a research project to have some sort of metal 3D printer. Stratasys is a 3D printing company that does diffuse deposition modeling, which is the same technology used by all the cheap printers at Home Depot, but they do industrial quality printers with parts that you can put in airplanes. And they can do parts anywhere from this big to the size of one of these tables. So they wanted to branch out into metals. All they had was plastics, and so they formed a team of 10 people it was a cross-functional team, a small cross-functional team that had all the technology people we need. We had mechanical engineers, electrical engineers, software engineers, and process engineers to build a 3D printer from scratch. And we were going to build this thing to basically leapfrog the current market, because as of 3 years ago, in fact still today, the 3D printing market has been kind of moribund. There hasn't been a whole lot of progress done in close to 20 years. 3D metal printing was introduced in the late 90s and hasn't progressed much since then. Anyway, so we worked for a couple of years at Stratasys on this project, and then Stratasys decided that no, we really don't want to do that. Spun us off as a separate company, which we call Vulcan Laboratories. And we progressed there for about a year or so, and then Vulcan Laboratories personnel and equipment was acquired by EOS. So, but at that point, the project hit the pause button, soon to be. We'll probably start it up again, but at the moment the project is not going anywhere. Anyway, so I'm going to run over what we did, how we did it, and how far we got, and why we did it. So without further ado, first a small introduction. The technology we were using is called powder bed fusion or selective laser sintering. It was invented at the University of Texas in the late 80s. It was commercialized here in Austin, Texas, by a company called ETM Corporation, which I actually worked at for about 6.5 years. That's why I came to Austin in the first place. The basic idea behind it is it's a layer-wise manufacturing process. And so you have this piston that, for every layer, you drop the piston just a little bit. One layer of material that you want, that's typically on the order of single-digit thousandths of an inch, so anywhere between 4 and 5, 6 thousandths of an inch. Then you use this, in this case, it's a roller to move a layer of powder across the bed, so you now have a nice uniform layer of powder on the bed. Then using a set of galvanometer scanners and a laser, you scan the laser on the cross-section of the part at that layer and melt it. So, and then you wash, rinse, and repeat, you slowly build up the part by selectively melting each layer at the places where the part is. Now, it has a lot of technology that's very similar to other things. Since it's a layer-based technology, you've got to get a part, you've got to slice it into things, you've got to make the regions on there, you've got to generate the raster fill vectors, and that's all more or less the same thing that almost all 3D printers do. The place where we were trying to innovate was a lot of this is basically open loop control. And so say if you take a cross section here right at the part bed, you got the laser coming down and it's melting, and you got this melt pool here, D, which It's usually run just open loop. Most people will scale the power of the laser with the speed you're going to kind of keep the power density the same. But that's about it. I mean, it turns out there's a lot more to it than that, because a lot of times you'll overlap the vectors next to each other will overlap, and depending on how fast you get back, the part may have cooled down or may not have. So the temperatures at the melt pool can vary quite a bit over the course of the part. And we wanted to actually monitor that melt pool to start with, and then actually control the laser power based on it. We also wanted to do things like, instead of one laser, use two lasers. Now, there are commercial machines that do that, but we wanted ours to be synchronized, so we could actually do things like, well, I don't want the part to melt, to cool off quite as fast, so I'll run one laser right behind it at a bigger spot size and kind of cool it off slower, so I get different material properties. Or maybe I want it to heat up a little better before the laser hits it, so I run the laser ahead of it to warm things up. Things like that. So we had quite a few things we were thinking about. I just mentioned the melt pool monitor, part bed temperature. One of the problems that these machines have sometimes is something called a short feed, where if you don't put enough powder in front of the roller, it gets halfway across, runs out of powder. And the reason that would happen is when you melt the part, it actually compacts a little more, because your powder typically is like 60 to 70% dense, but your melted part is 100% dense. So so if you have a huge amount of parts on the part bed, it's going to take more power to cover it the second time than if you have nothing. So you have to vary the amount of powder you put on, but at the same time, if you put too much, you might run out of powder before your bill's over. Because once the powder's gone past it, it's gone past it, it's into the overflow bin and, onto something else. So depending on whether your algorithms work well or not, and they do pretty much work well, because, they've been doing this for 20 years. But it still happens. And we wanted to have basically a camera on the part bed to say, okay, did you run out of powder? And the appropriate image processing and stuff. And for some reason, no one's ever done that. I already mentioned feedback that the machines use metal powders. Metals in powder form are very dangerous. Most people don't know it, but aluminum powder is used to enhance explosives. It's also used in fireworks. In fact, at DTM, when we first tried to order some aluminum powder, not knowing this, we ran afoul of all sorts of federal regulations, because you're basically buying explosives. And it is not unknown for people to, when you're doing this process, you're melting the metals, you've got a big plasma plume, you're throwing powdered metal up into the air, and since you've got air flowing across your chamber to keep the smoke down, at the same time, you're going to be picking up these metal particles in your atmospheric filters. Well, it's not unknown for people to pull out a filter to change it, and it bursts into flames. So we wanted to fix that. There are procedures to keep that from happening normally, but not a month and a half ago, somebody at Boeing didn't follow procedures. Fortunately, he was not hurt. Anyway, so on to our philosophy. And this is sort of a guiding philosophy I've had for a long time, and that our team came up with it kind of independently. And it's generic to just research in general. The first one is extremely important. When you want to do something new, don't start out with saying, what can I do? Start out with saying, what do I want to do? And it is amazing how often you can do what you want to do, even if people tell you otherwise. When I was first working here at NI, my first job was to write a soft front panel for the NI scope devices. Last time I checked, they were still using it. It's 20 years. Anyway, but one of the problems was LabVIEW at the time was very, very poor at handling large data sets. But the NI scope devices, one of their selling points is 32 megs of data. And so I had to be able to handle a wire with 32 megabytes of data on it and display it on the screen, write it to disk, all without choking a computer which only had 128 megs of RAM, because this was 2000 and we were using Windows 98. Or Windows 2000 if you were lucky. Anyway, so I figured out how to do that. despite the fact that people told me, no, don't do that, you're wasting your time. And the nice thing about doing a no compromises approach is if you do something that someone tells you you can't do, it's often very useful later. And I use that information to gain several contracts that just wouldn't have happened. And I gave talks on it at NI Week for probably close to a decade. I wanted to stop. It's one of those things that I didn't set out to do, but it's, the project required it, I did it, and it ended up having a lot of benefits outside of the project. Second point is use a generic core appropriate to your problem. The reason you want to use a generic core is that since this is for R&D, things are going to be changing. You don't know everything when you're going into it. So if you use a generic core, such as the actor framework, you can plug things in and out very easily without having to rewrite your entire infrastructure. And the second point is basically along the same lines, modular loosely coupled design. You don't want to have to rewrite your whole infrastructure every time you change something. And once again, the actor framework is a good example of how you can do this without having to reinvent the wheel. Now, obviously, you don't want to use the actor framework on a small embedded processor. And we were using a small embedded processor, so I didn't use the actor framework in this particular case. But like I said, generic core appropriate to the problem. I can't tell you which one to use because I don't know what your problem is. Anyway, document your interfaces. We had multiple things in multiple places and multiple users. And when we created an interface between two parts of the program, we documented it. Now this could have been as simple as parts of our program uses C#. We had interfaces, so we had actual interfaces that we could just document in the code itself. Other things, we were using commands over TCP to communicate to other things, and we documented those packet protocols and everything fairly extensively. And last but not least is incremental progress. Don't try to do everything at once. It's always best to start with a smallest element that you can get that actually works, get it working really well, and then add the next piece to it. And yeah, that's right out of the Agile Programming Manifesto, but it works. Okay, so these are I kind of look at these as normal R&D steps. The first thing is you gather the requirements, and ideally you should be getting these requirements from your customers. In our case, it was very easy. The leader of my group ran a service bureau up in Belton that had over 100 3D printers on the floor, and currently he had five metal ones and about 80 plastic ones, and then a smattering of other things. So all we had to do was find out what customers wanted, and just to walk out on the floor and ask his operators, is this a good idea? And they would tell you in no uncertain terms very quickly whether or not it was a good idea. So asking your customers what they want versus walking back and asking your engineers what they want is very important. Now, asking the engineers what they want is actually sometimes useful because engineers will often come up with things that customers will never think of, because a lot of people will get involved in, okay, this is the way it works, this is what I want to make it work a little better. They won't think of what happens if I do X to make things way better. Engineers are better at that kind of thing. But once the engineer asks you, then you go ask the customer, what would this do better for you? So, it's kind of a give and take. The second one is a point that was brought up earlier, and I consider it kind of the crux of the whole going fast. Is when you initially design your infrastructure, design it, now that you've got your requirements, to support all the requirements. Now this is not implementation, this is design. So you don't have to write all this stuff all at once, but you have to design your infrastructure so that it will support all the requirements that you have, and hopefully some that you don't know about, because those will happen. And that gets you back to the generic core thing. So you can, so you have the loosely coupled, you have the generic core, and it shouldn't be too difficult to design an infrastructure that will then support all your requirements. Then you start actually building that infrastructure, both the hardware and the code. In our case, this was an actual physical machine, and the code to run that machine, the motor and everything else. And you do this incrementally, just like you do everything else. So you you've got your infrastructure designed and so it'll support all your requirements. And you take a subset of that infrastructure that you need to support the minimal functionality you can get away with on your machine. You build that minimal infrastructure, the hardware code, whatever, and test the heck out of it until it works perfectly. And then you go and design your minimal working hardware code, the actual functionality you need. So you've got the infrastructure, then you've got functionality. You build and test that hardware code, test, and then you go on to the next piece. So start with an absolute minimal thing on a design that will cover everything. And now when you add more infrastructure as you need it, you're not bolting it onto the side and hoping it sticks. Instead, you're dropping it into the slot that was designed to hold it. And it makes a world of difference. You spend all your time writing new code and writing new functionality instead of going back and rewriting all your infrastructure just so it can barely design the next thing. I've been on projects that actually did that. I've been on projects that actually didn't go back and rewrite the infrastructure and work plug-in code so badly that it basically killed the project. I mean, well, it didn't kill it, but it killed it in the marketplace because the performance was so poor. Anyway, so wash, rinse, repeat. So what did we do? Okay, well, we gathered our requirements and we ended up needing a slow speed controller. So things like pushing the powder down, moving the pistons up and down that's fairly slow speed. That can be done. That can be done with a standard PC controller without any trouble talking to motion controllers. We needed a very fast controller to handle the laser control and the scan and drive the scanners around on the carpet. Since we'd be dealing with fairly large 3D files, we're going to be slicing them into slices, getting the outlines, doing the vector fills, and all that kind of stuff. So we needed a fairly good processor for that. So, being researchers, we picked stuff that was modular and replaceable. We did a standard PC running Windows 7. This was several years ago. It'd be 10 now. Don't start with obsolete equipment. For the slow control, and I picked a C-Rio 9066, which is one of those modular zinc-based controllers for the fast I/O. And that way, I mean, we had already picked out what we needed to do. We got the modular I/O, it fit, and then the PC could handle the rest of it. Now, the software platforms chosen. This is another very important point for making a project run fast. For the slow control and the GUI, we wrote it in C# because the guy who was writing that part of it didn't know LabVIEW, but he did know C#. On the fast control stuff, that was my part. I used LabVIEW RT and FPGA because I understand LabVIEW and I didn't understand VHDL and C or C++, which you also use to program these things. LabVIEW's faster than those anyway, so. Anyway, so that was who we chose. And 4 months later, what did we get? Actually, I said 6 months, it was actually 4. But, actually, no, this was 6. Okay, is it gonna run for me? Oh. This always works when I test it, it never works when I try to do it. Okay, so here's our first build. It's a fairly low resolution thing. Basically, this is a very minimal, okay, this is a very minimal functioning machine, but you can see that we had there it is. Okay, so this was, we didn't have a slicer, so we couldn't do arbitrary parts. We only had, although the code would support 2 lasers, the rest of the code would not. You can see the roller going across there. back. Anyway, the squares are very easy. You can hand code a layer like that, and you just keep feeding it the same layer and build up a bunch of squares. So, and this was a bunch of different, this was a design experiment with a bunch of different processing parameters. You can see some of the squares are darker and some of them are lighter. So this was an early experiment done about 6 months after we started. Okay. Okay, so here's our basic machine architecture. The main controller you see here on the right, or left, excuse me. On the left is the PC running Windows 7 with a C# controller. It ran, there are various and sundry heaters, slow motion control, the GUI, the atmosphere, running blowers and stuff to keep the smoke down, and then generating all the vectors for the galvo scanners. It communicated with all the hardware and the Serial 9066 through a gigabit Ethernet. We considered using 100 megabit because that's more an industrial speed, but we decided we didn't know what was going to happen and picked gigabit anyway, and later events proved to be a good choice, which I will get to. Then, so the motors and stuff will run off RS-485, which is just a Ethernet 485. And then the 9066, which is where all the good fun LabVIEW code was, it buffered the vectors, so the individual draw lines from the main controller. I did full up S-curve generation and generated all the little micro steps at each control interval, which was 10 microseconds. So this is being updated at 100 kilohertz, and then converted those over to the machine coordinates for the so that all the motion control was done in coordinates on the part bed, so that we could so we knew exactly what the speed of the laser was on the part bed. Yes.
So for the galvo, do you send like synchronous analog signal, or it has its own driver?
It had its own driver. There's a digital protocol. It's basically a serial protocol, one for each motor. And we had an X mirror, a Y mirror. We had a Z focus, because as you move around, the focus does change. And then we had a laser power as well. And those were all synchronized together in the FPGA and clocked out at 100 kilohertz.
Is like an F-theta lens?
We could. Problem with an F-theta lens is even though it keeps the focus the same, it keeps a focus on the part bed all over, the size of the beam changes as you get toward the edges. And since the sintering is highly critical on power density, we actually used an active focus so that we could maintain the same spot size all over the whole part bed. So essentially what we did is due to the way lasers propagate, the smallest focus you can get is bigger on the edge of the part bed than it is in the center. And so we picked the edge size as our spot size, and then if we moved inward, we would actually defocus the laser to keep it at the same spot size. And since it's a Gaussian profile, it didn't work. Anyway, so that's where we were. So now we had, that was basic, and so my next job was actually calibrating this whole mess. What you saw there was done with kind of we did the original smallest possible thing we did some theoretical lookup tables for the galvo positioning and the laser spot size, and it sort of kind of worked, but since the process is so dependent upon the laser spot size and power density, we needed some serious calibration on it. So we had to buy a laser profiler, so we knew what the spot size was. And then it turns out that calibrating the spot size was actually relatively simple. That's a process that we've done many times before. It's like a 15-minute procedure, and you can screw it up, but it's hard. The XY position calibration is a lot more difficult. And different manufacturers of 3D printers have very different ways of doing that. Most of them involve some sort of consumable, so I call it a stable substrate. Some people use stabilized paper at $25 a sheet. Some people use Mylar at $10 or $20 a sheet. And then you burn a series of holes on it, and then you digitize it, do some image processing, and then run through some math to get the actual lookup tables. We did something kind of back different. I had a stable metal plate with fiducials on it, and you scan those. I used the C-RIO to actually take data synchronous with the motion, so I could see when the laser struck one of the fiducials, and then and using that, I could automate the whole process. And so we took something that normally takes anywhere from 2 to 8 hours, or it can take several days if you have problems or don't do it right, aren't trained correctly, and made it an automated process that took about an hour. Now we had 2 lasers. The other advantage is the older processes where you would use consumables, you could calibrate one laser system, but then you have to take it off and put the other one in, and you don't have any XY. I mean, we're looking at calibration accuracies on the 2 3,000ths of an inch, so 25 microns, and you can't do that by just placing 2 pieces of paper in the thing, one right after the other. It's just not all that possible. So anyway, we automated all that, got that done. Laser power is another procedure. Turned out our lasers were so linear, we really didn't need to calibrate their power. All we needed to do is check their maximum power every once in a while. That's not true of all lasers. We were using fiber lasers for this, which is kind of standard for metals processing. CO2 lasers have a very complex power curve, those we need to calibrate. So if you do plastics, which is what CO2 lasers are used.
How often do you have to calibrate the XY position?
In theory, you should only have to calibrate it. They're all digital position sensors, so once a year is probably enough on a standard machine. Our biggest problem was we kept changing the optics. And so every time you change the optics, or if you change the distance from the part bed to the optics, you have to recalibrate. So we ended up doing it a lot just because we were in an experimental setup, but normally not very much.
That was the trade-off of, spending a month to automate something to save 8 hours, but it's only done once a year.
The biggest trade-off, the biggest reason for the automation was, I designed one of the automation. I designed one of the systems that used Mylar back, in the mid-90s, and there's a lot of room for making errors. I mean, I've seen techs forget to wipe the smoke off the Mylar after they burn the holes, and the smoke causes artifacts which then screw up the image processing and screw up the calibration. And then 3 weeks later, we get a call from the customer that something's wrong. And that happened just 3 months ago. So it's still happening. So yeah, automation is if you can automate something for this, and also customers like to be able to do this kind of stuff themselves. And if they can buy a $3,000 count plate, and it's a highly accurate plate. I mean, we're looking at thousands of inch tolerances, and be able to run a calibration just to verify that things are okay. Especially if you're doing defense work or something like that, there's a desire to make sure that your equipment is working as expected. Most of the fabrication houses that do this correctly will at least do spot checks of laser power every morning, and because it's easy to do. I mean, you just put the power meter in there, set it at something, it should be X power. If it's not, then you got a problem. And that's what we were trying to do with this XY calibration, is make it so that it's an hour procedure. You just drop the thing in there, click it before you go home, come in the morning, check, is everything okay? Yeah, good. And then we ran into our first big problem. The part piston, which drops every time it gives you the layer thickness and has to have very accurate motion stages to give you an accurate distance. The motors we had didn't have the control accuracy we needed. I mean, on paper they did. when we put them in the machine, they did not. And We played with those things for probably a couple of months before we finally just gave up and did a search for another manufacturer. Found one, retrofitted the machine with it, rewrote the drivers, but since we had modular loosely coupled software, it was actually a fairly easy thing. We didn't have to rewrite everything else. And the other thing, since we were using the C# code was using an actor framework. And so it was very easy, since we had this actor-like framework, to create models for the rest of the machine and simulate the rest of the machine, so you could walk off back in the control lab. You didn't have to have a machine, and you could just run the software that just ran the motors while basically running a build, because we had simulators for all the different modules, and so we could run a build and run almost any module in the machine separately, and that made it very easy to debug new things without having to tie the machine. I used the same trick in my laser lab to do both calibration and some other new stuff I'll show you in just a minute. So that writing loosely coupled software works. And then we rapidly added other functionality to it, since once you have a working machine, it's a lot easier to get things going. We did slicer support, so we could do actually 3D models. We added synchronization delays in the laser galvo data pipeline. Lasers respond a heck of a lot faster than galvo scanners, so the software was designed in a pipeline manner, so we can do things like that to it. And that was like a 2-hour process. I said, oh, I need this delay. Oh, okay, I'll be back. And, oh, I think it took as long to compile the FPGA as it did to actually write the code. We separated our GUI out. We originally were working on this engineering GUI, and you all know what that means. And so we got an actual operator GUI, and we separated it out as a separate process, because one of our requirements was I want to be able to control the machine from my office and not from the machine. And so we ended up just doing a TCP pipe to it, and that could be any place in the world, literally, if you had a valid TCP connection to the machine, you could run it. And the GUI model that we had before that was doing all the GUI was then changed into a simple message transceiver. So from the control systems standpoint, nothing really changed. It's still talking to this GUI model. And but the GUI is now translating the commands to TCP and bringing them back again. And I already mentioned the simulators. We, in the course of this, of building this thing, we created drivers for multiple lasers, multiple galvanometer scanners. I already mentioned the motion stages. And as we had originally planned, we swapped the C-Rio out for an SP-Rio. I had selected the C-Rio because it was basically the same processor and FPGA as you get on the SP-Rios. And we created a custom daughter board to give us more efficient I/O. And I was actually surprised at how slow the digital I/O on one of those C-Rios is. When we went to the SP-Rio, we went from a maximum speed of around 100 kilohertz, I think, or something like that, maybe megahertz, up to like, I think I got 40 megahertz signals out of the C-Rio, out of the SP-Rio, without any trouble.
So the SP-Rio is faster than the C-Rio?
It's not faster than the digital I/O available for it is. So the C-Rio is limited to those little plug-in C cards.
Right.
And I think those are going through either an SPI or an I2C interface. And so they're not all that fast.
Okay.
You can get, and the high-speed ones, I think, will go to maybe 5 megahertz. I can't remember.
I think 10.
10?
On 401.
Yeah. But to do the things I needed to do, I needed up to 40 megahertz. And I didn't need it in the initial stages, and I knew that, you know, this change was coming. So it was, of course, sort of a planned thing. But we start with this, make sure we don't need anything else. I've got plug-in modules so I can do it if I need to. And then we went to the SP-Rio, and everything was all custom I/O, and we were good to go. And here's what this looked like. How's this one? Maybe. No such. walked off the,
Okay, there's a screen at the back of the room.
yeah, it's behind that.
No, in the back of the room, there's another screen.
Yeah, no. Oh, okay, drop it in a second. Okay, here you see two lasers simultaneously, and it's also doing multiple parts. So there we are. So now we have a fully working basic machine. And so it's time to do something else with it. And our first thing we wanted to do was do the melt pool monitoring. So I took my code to the lab, and since I already had some data acquisition code from doing the calibration, I modified that so that I could also take data simultaneously with scanning the laser and look at actual temperatures on the part bit. Well, actually, it's just radiation from the part bit. We just had a single photodiode pyrometer that we had set up. We peeled a little bit of the laser of the beam off with a dichroic mirror, so we could look at a different wavelength than the laser was lasing. It's a fiber laser, it's 1 micron, and we looked at both really near infrared, like 800, 900 nanometers, and then also a little deeper out at 1.2, 1.6 microns. And what we got within the signal you see on the right there is what we got after about a week in the laser lab. There's a couple of tubular heaters there, just a picture of them, and then the IR camera display next to that, and then the right picture is a LabVIEW screenshot from the signal from the pyrometer that I was using the galvos to scan. And this is a good example of, we set the machine up to do this in the first place, and so making it was just dropping something into a slot prepared for it. A couple of weeks later, we actually had signals up on our GUI. That was a little more difficult because you're writing GUIs in C#. It's not as easy as writing GUIs in LabVIEW. And none of us was a C# expert. Okay, so we had that. What's next? The next is actually controlling the laser from that. And then we ran into a big problem. I ran out of fabric on the FPGA. Unfortunately, those little SB Rios don't have the world's biggest FPGA on them. And after doing 2 channels of two full lasers, so I had 8 channels of control on those things, and we were already monitoring laser power. Putting a PID on both of them was just the straw that broke the camel's back. And so at this point, we discussed various options, and we decided the best thing to do would be to take the motion generation, which we had been doing on the FPGA. I had actually originally tried it doing it on the RT side of with the ARM processor, but it simply wasn't fast enough. It was close, but not quite. And we moved it all the way down into the C# layer. So now, instead of sending just individual vectors up to the C-RIO controller, or the SB Rio, we were actually sending a stream of the little microvectors, each control point at 100 kilohertz. So we just increased our bandwidth by over a factor of 100, somewhere between 100 and 1,000 over the Ethernet. And so that's why it was a good idea that we had the gigabit Ethernet. We were still 100 kilohertz, 100 kilobit-ish. So we were still way under what the Ethernet would handle. But it was a little tricky getting all the buffers to work right and getting everything. And that's why we didn't do that in the first place, because we thought it would be a problem that we basically couldn't shuttle that much data reliably over an Ethernet. But when we were forced to do it, it actually turned out easier than we expected. Now, don't get me wrong, it took us roughly 3 months to do it because we had to port an enormous amount of code. Because all of that automated calibration code, that had been written for the C-RIO in LabVIEW, so I had to port all that back into C#. fun time. But anyway, it ended up the RT FPGA side was now much simpler. We were only using like half the FPGA, so it's now available for a lot of other stuff if we need to. And it gave us, and the calibrations were now running faster because all the processing was now being done on a fast Intel processor instead of that little one long arm. Because there's a lot of data modeling and stuff that had to be done in calibration. So that worked out really well. And so this is our new machine architecture. And you can see the major change in this is that the S-curve generation, the vector to microvector, and the coordinate transform have now been moved from the SP reel, which is now SP reel, so the C reel, over to the bank controller, and then the embedded controller here is now handling. It's still clocking the microvectors out, so it's still doing the synchronous I/O to run these, but it's also monitoring the pyrometer and doing laser power control of that stuff.
So your main controller is a PC or?
The main controller is, yeah, just a standard PC. We had 3 different PCs of varying ages. One was like 5 years old, and then a couple of fairly modern ones as of 2015.
Is it reliable enough to do like long process time, say like 24 hours?
Oh, easy. Oh yeah, we did 3-day runs on it. You do have to turn off things like Microsoft updates and because we did have that capability on us once. But yeah, we didn't have any trouble.
And I'm wondering why don't you dump everything on the compact radio or SP radio as a standalone? So once you deploy it,
it doesn't have enough resources. It simply doesn't have enough resources. Is the reason. For example, I just mentioned I originally tried to do S-curve generation on the RT side of this. It wasn't fast enough.
like hard drive wise or RAM?
No, time. It couldn't keep up. It couldn't generate the microvectors fast enough.
Is it per layer or per?
Well, it was it basically I had a line and it sent it a line and I could have buffered it per line and then sent it over, but that introduces delay. If it's not keeping up, then that means it's slowing our build down, and we didn't want that. So once we started building, we wanted it to go as fast as the actual hardware could go, and the RT side couldn't keep up with the hardware. Now, a faster processor on the RT side would have made that possible, and we could have done that, but PCs are very cheap, and getting a faster processor over there would have been a $10,000 investment, because I would have had to go to a PXI system and then a plug-in FPGA card, and those started at about $10,000. And so how did we do? Here is a slide from a presentation we made at the Solid Freeform Fabrication Conference last year, end of summer, just before we were acquired by EOS. And on the right there, you see a heat map of a part. That's actually what the part looked like. It's a 3D part built using closed loop control. And then on the left, there is the heat map of the same part built using open loop control at what we thought was more or less the same laser power. And you can see the obvious variations on the right, onto the left. Anyway, so that worked pretty well. Now, this was still in its research phase. This was not what I would call ready for prime time, but we did get to the point where we could build parts using closed loop control. And to my knowledge, no one has yet released this at all. And what's even more amazing is that this original process was patented in 1993. Someone did this in 1993, patented it to try to get people to do it. And you may ask, why wouldn't they? It is tough. There are some major problems that we found in doing this, which we found solutions for, and would have been available in the mid-90s as well. And especially for both industrial and military uses, having verification that your build is actually what you think it is and having good control of your process is extremely important. And I think the only reason no one has done this is because no one else has done it. And as long as you don't have to do it, there was just an inertia. That's the only reason I can see why no one else did it, because it wasn't particularly hard. Anyway, at that point, we got acquired in the process, and we hit the big pause button on the project. I'm reliably informed that the go button will be pressed sometimes next year, so we'll be able to continue our thing. So, my blueprint for R&D success is plan for what you want, not what you think you can get. Use a generic core and make sure you change it if you have to. I mean, the fact that we had to refactor and move serious functionality from one place to another, that was a core infrastructure thing. But it did not affect anything more than just one module on the main controller side, which is just the laser scanner module. Just got a lot more functionality. Module loose and couple design, document your interfaces. Our biggest interface we had to document was the command packets from the main controller to the galvo scanner, and we kept those up to date because two programmers doing two sets of code and needed to know. And lastly, make incremental changes. Don't try to do everything at once. So we built it up slowly, and we were able to just keep building because we didn't have to keep refactoring code in the background constantly just to do any small thing. We were just dropping things into slots that they'd already prepared. Questions? Yes.
So why not hire a LabVIEW programmer?
We didn't have money at the time. Because our C# programmer was also our controls engineer. And finding a good LabVIEW programmer was also a good controls engineer. Oh, he was also our programming expert. And so we had a lot of cross functionality in our team. So I was a LabVIEW programmer, but I was also the laser optics guy. I designed all the optics for the system and the calibrations and stuff. And whether or not we can actually do it.
So what's the major hiccups when you interface C# and C regular?
We didn't have any real major hiccups. And the reason for that was we kept a very clean break at the TCP level. Since we used just bog standard TCP, and then we didn't use binary packets because we knew we were going to have something like XML or even JSON would have been too big, because it's just when you're shoveling that much data over, you need to keep the size. And so if I had known about it earlier, I would probably there's a API called Protobuf that is binary and does automatic code generation for you on the C# side and on a lot of other languages too, Java, C, Python, and there is a LabVIEW plugin available for Protobuf. I don't know if it does full code generation like the C# does. You know, if I had known about that earlier, I probably would have used it because what we ended up doing was very simple. So yeah, we kept it very short out there. I have had experience in the past with working with programs that are basically calling LabVIEW code from C#, calling C# code from LabVIEW. I can tell you that's a disaster. Don't do it. Do not do that.
The network you described is an internal network to the unit, right?
Yes,
Because you described another network that people remotely connect to the main controller.
right, that would be just the standard. The gigabit Ethernet I have on here is a private network. It's got fixed TCP addresses. So there was no finding anything required. Just, you know, if you want to talk to the controller, you go to address 50. You want to talk to the RS-485, you go to address 40, and et cetera. and we had very well-defined ports, and that was all documented. We kept track of that, so we could easily access the record.
Usually takes me, like, for me to really disconnect the case.
And then you had another TCP system from the microcontroller to the remote system.
We could, I mean, it was just a standard internet connection, World Wide Web.
So it's like a web page that you were hosting?
It would have, no, the actual, what we did was we would log into the machine, we could use the TCP address and port of the machine, and we used double auxiliary network. It would have been a little trickier to try to get to it, say, from Hong Kong. But I think you could have done it, but it was we might have needed a relay or something. But yeah, it was just we just used a TCP address to talk to them.
And that is a separate application.
That was a separate application. We could have written in anything. We had originally envisioned it being a JavaScript, being an actual.
I've observed that.
We got tossed out from Stratus, we lost all our JavaScript.
They're gonna tear down the walls.
Oh, that's fine, I'm done.
All right.
Thank you.
Yeah.